every star in the night sky burns because of an invisible furnace hidden inside its atoms. The same nuclear engine that lights the cosmos also drives the devastating power of the atomic bomb. This is the story of how matter holds itself together and how it sometimes violently tears itself apart. Begin with your hand, trillions of atoms densely packed into every fingertip. Now dive inward. Each atom is mostly empty space, with a tiny, blazing nucleus at its heart. At the core lies the nucleus, a tiny, ultra-dense drop of matter. It is built from protons and neutrons packed so tightly that the nucleus is about 100,000 times smaller than the whole atom. But there is a problem hiding in plain sight. Every proton carries a positive electric charge, and positive charges fiercely repel each other. Inside the nucleus, dozens of these like charges are crammed together. By all rights, the whole structure should explode apart. So, what invisible glue is holding it together? At distances smaller than a proton, another force awakens, the strong nuclear force. It acts like an invisible glue, overwhelming electric repulsion. But only when particles are almost touching, then it vanishes beyond a trillionth of a meter. In our universe, 4 fundamental forces choreograph the motion of everything. Gravity shapes stars and planets. Electromagnetism binds atoms and powers light, chemistry, and electricity. Deep inside the nucleus, the strong force glues protons and neutrons together, while the weak force quietly triggers radioactive decay and fuels the sun. If we dive even deeper still, each proton and each neutron is itself a tiny swarm of even smaller particles, called quarks. These quarks are bound together by gluons, carriers of the strong force, in a restless, seething dance described by quantum chromodynamics. Whether a nucleus is stable is a delicate contest between the strong nuclear force pulling everything together and the electric repulsion pushing protons apart. Neutrons act as spacers. Too few, and protons repel each other apart. Too many, and the strong force can no longer bind the swollen nucleus securely. There is a hidden cost to holding a nucleus together. Some of its mass simply disappears. Einstein's E equals mc squared tells us that missing mass reappears as binding energy, the energy glue locking the nucleus in place. At the dawn of the 20th century, uranium salts baffled scientists by fogging photographic plates even when sealed in darkness. These invisible, deeply penetrating rays, first studied by Henri Becquerel and later Marie and Pierre Curie, would soon be named radioactivity. Radioactivity is what happens when an unstable atomic nucleus slowly reshapes itself into something more stable. It does this by emitting matter or energy, tiny particles or packets of radiation, carrying away excess energy and imbalance. One common path to stability is alpha decay, where a heavy, unstable nucleus ejects a compact bundle of 2 protons and 2 neutrons. This alpha particle is essentially a helium nucleus, and by throwing it away, the original atom loses 4 units of mass and 2 units of positive charge. In beta decay, a neutron can transform into a proton, driven by the weak nuclear force. An electron and an almost massless neutrino shoot out, carrying away charge, energy, and momentum. In gamma decay, the nucleus remains the same element, but releases excess energy as a flash of high-energy light. These gamma rays are the most penetrating form of nuclear radiation, and they require thick lead or concrete shielding to stop. Radioactive decay is random for each atom, but predictable in large crowds. The half-life is the time for half of the nuclei in a sample to decay. Plot the number of undecayed atoms over time, and you see a smooth, exponential curve, dropping by half every half-life, like a steadily dimming lantern. heart of every nuclear reaction lies Einstein's insight, E equals mc squared. Even when just a tiny fraction of mass disappears, that lost mass turns into a colossal burst of energy because c squared is a staggeringly large number. Nuclear fission occurs when a heavy nucleus, like uranium-235, absorbs a neutron and splits into two smaller nuclei, releasing extra neutrons and vast energy. Those freed neutrons can strike neighboring nuclei, triggering a chain reaction that, if left unchecked, grows exponentially in microseconds. In reactors, control rods and coolant tame this chain reaction, turning steady heat into electricity. In bombs, all moderation is removed, and the same physics unleashes a devastating, runaway explosion. Fusion is the opposite of fission. Instead of splitting heavy atoms, it forces light nuclei, such as hydrogen, to merge into heavier ones. In the cores of stars, temperatures of millions of degrees and crushing pressures slam these nuclei together, overcoming their electrical repulsion and releasing vast amounts of energy. In the hearts of stars, like our Sun, hydrogen nuclei are crushed together to form helium, releasing torrents of fusion energy. Every second, our Sun converts about 600 million tons of hydrogen, turning 4 million tons of mass into pure radiant power that illuminates the solar system. Recreating fusion here on Earth means bottling a tiny star, requiring temperatures of over 100 million degrees. To contain that furious plasma, we twist it with colossal magnetic fields in tokamaks, or hammer tiny fuel pellets with stadium-sized laser arrays. Across billions of years, stars act as cosmic forges, fusing simple hydrogen and helium into heavier elements deep in their cores. In their final, violent breaths, massive stars explode as supernovae, scattering newly forged carbon, oxygen, and iron back into space to seed future planets and life. When massive stars die in supernovae, their collapsing cores ignite torrents of nuclear reactions that forge elements far heavier than iron. In even rarer neutron star mergers, matter is squeezed so intensely that rapid neutron capture builds gold, uranium, and many of the universe's heaviest elements. In hospitals, carefully chosen radioactive isotopes reveal hidden tumors and track blood flow, allowing doctors to diagnose disease without a single incision. Radiocarbon dating times the decay of carbon-14 in ancient wood and bone, turning atomic clocks into archaeological timelines, reaching back 50,000 years. Nuclear reactors split heavy atoms to generate steady, carbon-free electricity, while powerful gamma rays image welds in bridges and pipelines, inspecting metal the way X-rays see bones. The same forces that light the stars can also harm us. Ionizing radiation damages DNA, and long-lived waste must be isolated for thousands of years. But physics also gives us safeguards, dose limits in millisieverts, shielding with meters of concrete and water, and robust reactor designs that shut down automatically. Informed policy rests on this understanding, weighing measured risks against benefits, and deciding, in a scientific way, how nuclear technology fits into our energy and safety future. From quarks, bound by the strong force, to blazing stars and fragile societies, nuclear physics links the smallest scales to the fate of worlds. By understanding this hidden engine of matter and energy, we not only read the universe's past, but also help choose the nuclear future we build here on Earth. As the universe darkens around us, the stars remain, silent reactors fusing hydrogen into light. Each point of light above you is a nuclear engine, still burning, weaving the elements that make planets, oceans, and you.